Hello and welcome back to Let's Code Physics. We are picking back up with our wave function evolver. I've reset it to the simple case of a harmonic oscillator, an x squared potential energy, a displaced Gaussian for the initial wave function. So it's just bouncing back and forth. The expectation value is behaving like a sine or cosine or some variant thereof, like you would expect. I've also added in a label here to keep track of what everything is. The red is the real part of the wave function, green is the imaginary part of the wave function, white is the wave function modulus squared, so that's the actual probability density. And I've added on this yellow graph. It's technically not supposed to be there because it's graphed with different units. Although technically the psi and the psi squared shouldn't be on the same graph because they are different units. So I've already broken my own rule there. But the yellow is a rescaled version of the potential energy. So this just gives you an idea of the shape of the potential energy, because we're going to be changing the potential energy shape today to get an idea of how the wave function behaves differently. So we've seen this scenario before. The potential energy is a harmonic oscillator, an x squared parabola centered around 0, and we're going with the simplest lowest energy level stationary state, just a Gaussian that's been displaced over to the left by a little bit. But speaking of displacement, so this thing is a stationary state that's been displaced. So if I displace the potential energy, I should be able to get my stationary state back. Because I have all of the factors and everything there. So let's try moving the potential energy to the left a little bit. So now I've got a plus 0.5 on x to match this plus 0.5 on x. So I should get a stationary state again. And again, I do. To within, the tolerance of the code. The white is oscillating up and down a little bit, but it's overall maintaining the same shape. Most importantly, that peak is not moving terribly much, to within the error of the code. The expectation value is staying right around -0.5. It's staying right around the location of that peak. Again, its initial location, or the initial location for the peak. So this is cool because really the choice of where you locate your axis shouldn't matter, right? Because where the axis is located is something we choose. But if the yellow thing, the potential energy, moves along to the side, I should be able to move the stationary state with it and still get a stationary state. We can even try that out with some of our higher energy stationary states. Let's try the 2-lump one. So same thing here. Again, it's centered around the x equals -0.5. This thing is waving a little bit due to the error in the code, but that's actually pretty decent. And again, most importantly, the shape of the probability density, the white curve there, is staying the same. And the real and imaginary parts, they're just shifting weight back and forth between each other, like you'd expect with a stationary state. So that's pretty cool. Let me let's put this back to the lower energy displaced stationary state. So the harmonic oscillator is kind of the standard test in physics. It's the problem that we know how to solve in classical mechanics, the problem we know how to solve in quantum mechanics. So anytime you develop something new in physics, you try it out on the harmonic oscillator first. But what if we tried a similar but very different problem? What if we tried I think the technical term for this is a quartic oscillator, u equals x to the 4th instead of x squared. So it's got the same general shape. You'll see that the u curve has very much the same general shape, but our wave function is not nearly as nicely behaved, right? So this wave function is no longer a stationary state of the potential energy. You notice that the potential energy has this much broader shape to it, and so it's breaking up into these sort of constituent wave function patterns there. So you can see it's got these different wave interferences going on, and our expectation value is behaving rather differently. It's got the same general shape, right? Because it has to bounce back and forth, because if you took a classical particle in here, you'd expect it to roll back and forth. But it's not going to roll like a sine or cosine anymore. And so this thing is rolling back and forth a bit differently. In fact, maybe I should have started with a simpler case. Let's start out with the wave function centered at 0. Maybe that'll fix the problem. It won't. And again, you know, it starts out again in the middle, and it's shifting weight kind of back and forth. But what you notice is we are getting some oscillation in the expectation value of x, but it's very, very small. So while this thing is changing, while the wave function is changing and oscillating back and forth, it's maintaining its symmetry, right? So this thing, the red curve and the green curve, and therefore the white curve, are still maintaining their left-right symmetry, or their positive-negative symmetry, because this potential energy is positive-negative symmetric. It's an even function. And this thing started out as an even function, so because of the way the Schrodinger equation is set up, this thing has to stay an even function. It has to stay symmetric, which means that our expectation value of x has to stay at 0. Now, it doesn't look like it's staying at 0, but it's staying 0 to within 1 part in 1,000, which is pretty good, and it looks really good if you zoom out like this. Oh, look, it's hardly changing at all there. That's not changing at all. I use that trick in lab sometimes when students get data that's varying like this, and I say, yes, but zoom out. Is it really doing a lot when you put it on a real scale there? Cool. So that's what happens when we promote the x to the 4th power. What if we promote x to the 6th power, right? So we can go up even higher. Oh my, we got a result that was too large. Well, that was different. What, can I see the, oh my, so the wave function shot off to the side a little bit. Let's see, I suspect that's because the thing is becoming broader. So what if we increase this thing a little bit? Let's put a factor out in front of it. Okay, it got a little bit farther this time. Now it's telling me there's an index list out of range. That's weird. Okay, let's give this one more try. Maybe I should have tried this one before starting the recording. Okay, maybe that's not working out so well. All right, well then, that's just fine. We will leave that one for another day. The thing I'm most interested in, I mean, it's going to be another version of the x to the 4th, right? It's going to split apart and do its little dance and everything. But what I'm really interested in is some tunneling barriers. So what we're going to set up next is a potential energy where on the left-hand side we've got a flat u of 1.0, and then on the right-hand side we've got a flat u of 10. So there's going to be this sharp a jump in the potential energy. That's what you'll see in the left curve here. So it looks like this step here. Now here's where we've got a little bit of an artificial case set up, because I've got these endpoints at the left and the right fixed at 0, and so the wave is kind of hitting an infinite barrier there and bouncing backwards. What you notice, this thing, it doesn't maintain its left-right symmetry, because this function is definitely not an even function. What you notice is if you pay attention to the white, and I might turn off the red and green for this to be able to see it better, but if you pay attention to the white curve, most of the weight, most of the probability is staying on the left-hand side. It's staying in that lower potential energy area. In this higher potential energy area, there's not really a whole lot of probability over to it. And in fact, why don't we go ahead and turn off the why don't we go ahead and turn off the psi real and psi imaginary parts there. Let me just take care of that really quick. Psi real dot plot. We will comment these out. There we go. This is just to get rid of all of these so that we can just focus on the the modulus squared. All right, so I should be able to see, let's try psi m, make sure I got all of those. I did not. There's one there. Okay, I think I got all of those. Let me make sure. I think the psi mags should be fine. Yes. Okay, all the psi mags are fine. Okay, let's try that again, and this time we can focus just on the probability density. So you see, the wave kind of scatters away from that barrier, right? Because if you think about it, the energy of this thing lies somewhere between the the lower energy over here and the higher energy over here. So if you think about it, classically, if I had a particle and it started out this way, the particle would only be allowed over on the left-hand side. It would not be allowed to go on the right-hand side. Quantum mechanics doesn't have quite such a strict restriction. Strict restriction? Doesn't have quite a strong restriction. And so quantum mechanics says the particle can be in the classically forbidden region, but it's going to be with less and less probability the farther you go into the forbidden region. We can even see this better if we switch back to our display stationary state, because this one, it's starting out symmetric, so it's starting out with equal weight in the allowed region and in the forbidden region. So let's start it out with it mostly in the allowed region. So you're going to start out with the probability density primarily over here. You can see it's going to be bouncing back and forth in this area. Once it hits this wall, once it hits this barrier, it's going to tend to bounce back. You can even see that in the expectation value up here. So this is expectation value of x versus time. You notice it's always negative. It's bouncing back and forth between negative values. It's not even getting very close to the barrier because of the way the wave is interfering with itself. So it keeps bouncing back and forth over here, but there's a little bit of probability that leaks in over here. And if you take a look, it's got this almost kind of exponential shape to it, because if you were to take the stationary state solution for this thing, you would see that it's got this sort of exponential decay into it. Oh, there's a really nice exponential looking decay there. And so the farther you get into this excuse me, into this barrier, the less likely it is for the particle to be found there. You're never going to see, at least I don't think you're ever going to see, the expectation value creep above 0. In fact, it hasn't even gotten back up to the -0.5 that it started with. We might even try displacing this a little bit more. So let's say we displace this all the way over to -2, so well within the well away from the forbidden region. Here you see it's moving a little bit this way, and then it bounces away from the barrier. You take a look at the expectation value. There's only a tiny little bit of probability in the in the forbidden region. Most of it's in the allowed region, but it can go through. It can go into the forbidden region. It's just got to increase. It's got an ever decreasing probability of being in there. But what this means is that if I were to say take this scenario and lower the potential barrier over on another side, like let's say I reduced it back down to 1 here, there is a probability that the particle can leak through to the other side. So let's give that a try. So let's say we only have this barrier going to let's say 2.5, just to get it, almost get it a little less than halfway through there. So let's say it's only going to be up to 10, potential energy is only going to be up to 10 if x is less than 2.5. So if x is less than 0, the potential energy is going to be 1. It's going to be that lower value. In fact, I might even reduce that down to 0 just to make this a little bit easier. So let's say if x is less than 0, the potential energy is going to be 0. It's going to be flat. It's just going to be at the floor level. Otherwise, if x is less than 2.5, so if it's between 0 and 2.5, you will be 10. And otherwise, right, so in any other case, let's say that u is back to 0. So this is if it's to the right of that 2.5. So let's take a look at our shape here. Okay, so we get this block that we have here. Again, the wave function is starting out over on the left here. It's bouncing back and forth, and it's allowed to go into the forbidden region a little bit. If it could be in there with a little bit higher probability, we might see it make it all the way over to this side. Let's give it a second. I'm probably going to need to narrow the potential energy a little bit more. Yeah, it is not making it through there, so let's make this a little bit narrower. Let's take it all the way down to 1. So the barrier only has a width of 1 now. Probably going to need to narrow it again, but we'll see what happens. So you see it's got again this sort of exponential decaying probability of getting inside. Let's see, is there enough to get it through? Oh, another thing I can do is that I can give the particle more energy. Let's see. Could I do that by stretching it farther to the left? I keep thinking in terms of harmonic oscillator. Let's say we start this thing over at 4. Is that going to give it enough energy to get through? No, that doesn't really change anything about the energy because the potential energy is flat out here. I was thinking of the harmonic oscillator potential energy. So let's actually change that back to 2. Let's see. Let's try narrowing this a little bit more. Let's decrease it. Let's decrease it down to 0.2. Basically, what we're doing now is a tunneling experiment because we're trying to see what we can change about this barrier to get the particle to leak through. And we've actually got some success now. You see that the particle, it's not just decreasing here. Well, it just went down to 0 there, but that's because the wave is going up and down. But it's got a non-zero probability going in through the barrier here and making it to the other side. So by making the barrier narrower, I can have a probability of it going through, and then of it going, going deeper and deeper into the barrier, and then making it to the other side, to where I've actually got a pretty significant amount of weight over here on the other side. Now, of course, there's also a probability that weight is going to transfer from the right side back over to the left. So we haven't seen this thing get too much higher, but it is creeping up a little bit higher, the expectation value there. It's kind of reflective of the symmetry here. Oh, this thing is going up. It might make it to the other side. Oh, it's downturning. Oh no. Oh, there it goes back. Oh, yeah. So this is kind of fun to watch because basically what we're doing is, you can imagine if it were a single particle and we were kind of leaving the system alone, this is the probability of where we would find the particle. Or if you think of it as a shower of particles, you imagine, putting in a beam of particles on this side. This is the probability that they'll come in through the other side, even though they don't have enough energy to make it. Let's see. What about this thing? Is it going to make it? Let's see. That actually gives me another idea to try. What if on the left-hand side, instead of making it just a flat 0, what if we made this the harmonic oscillator again? Let's see what that does. Because what that's going to do is that's going to give this thing a little bit more energy. Oh, and it definitely has enough energy there to make it to the other side because it's rolling downhill toward it. Okay, so that was pretty fun. Let's actually make this one a little bit higher because that gave it way too big an advantage there. Let's increase this U. Let's see, I can increase... Let's try increasing the U. I'm a little worried about that because sometimes the code freaks out with too high a value of potential energy, but let's see what happens if we double that. Okay, so we start out with a probability over here, and it does leak through to the other side. Oh, I actually get more weight on the right side than I have on the left side now, again, because I've given it a high enough energy there. So that's kind of cool. You notice over here, it's messed up the Gaussian shape, right? The Gaussian is no longer a nice stationary state anymore, or it's no longer staying in the Gaussian stationary state over on this side. So that's pretty cool. Let's see. Let's try making... All right. So we've given it enough of an advantage. So let's make this thing wider again. Let's see if that... let's see how that impacts it. Okay, so we don't get quite as much coming over on this side. So you can imagine so this thing is bouncing back and forth just like you would expect a harmonic oscillator to do. And basically it's hitting a wall when it reaches 0 here. And so it's bouncing back. But there's some particles, there's some probability leaking through the wall over here. So you can imagine this thing is trending upward each time. So with each oscillation, the maximum of the expectation value is getting higher. We might eventually get to see it creep past the barrier there. Let's see. Ooh, there it went a little bit higher. Come on, are we going to make it? Are we going to make it? Almost. Oh. So another thing that I could change about this wave might be to give it more energy initially. The way I could do that, just think of this in terms of a spring. I can pull it back farther. So, oh, did it make it? Oh, it almost made it. Oh, man, I want to give this thing more energy, but I want to give it a shot to make it over. Oh, it just went down again. Okay, so let's pull this spring back a little bit more. Let's pull it back to the 2.5 mark. So now I'm giving it more energy total because I'm pulling the spring back more. And here it comes rushing toward the barrier. Didn't quite make it past, but that's not going to stop it this time. Got a little bit higher this time. There's a little more weight getting transferred over to the right. Of course, there's always weight going back from the right over to the left side. This is really cool to watch. This is not your average sine or cosine, definitely. Let's see. Let's see. I need to add some wave sound effects to this. Let's see. Let's try that. Let's try pulling it back a little bit farther. Let's pull it. You know what? Let's do like Mythbusters. Let's blow it up at the end. Let's pull it all the way back to 4. Invalid value encountered in square root. I wonder what that means. It didn't stop the code. Oh dear, the code is the results are very jagged now because I pulled it all the way back here, and there's not enough space back here for that initial wave function there. Not sure what's going on with the invalid entry in the square root. I'll have to look at that later. But yeah, you can see that the motion's getting much more jagged now, which means I should. Oh, actually, what I really need to do is check my epsilon value. So epsilon is supposed to be small. Oh no, it's the same as it was before. Yeah. I guess it needs to be a smaller one. Okay. Well. Oh, another thing I could do, though, I could put it in a higher energy state. So this one has a higher energy state to begin with. This is the 2-lump one. Let's pull it back to, say, 1. And let's see what happens when this thing rams against the gate there. Oh, that was very different. That one started over on the right-hand side. Did I do that right? Oh, you know what? No. Oh, I need to change this part as well. Right. So if I move one of the x's, I have to move both the x's. So that was not the appropriate stationary state. Okay, so there's a 2-lump system. It didn't stay 2-lump for a while. So this one's got more, this state has more energy in and of itself, so it's able to get more probability leaking through to the other side. Still not quite reaching the right-hand side. Let's try pulling the spring back just a little bit more. This will probably be my last attempt here. Is it going to make it? Is it going to make it? Oh gosh, it got deflected. Okay. All right, then let's lower the potential energy. Let's not make it too easy on him. Let's give him 15 potential energy units. Almost there. Almost there. Okay, let's make it a little bit easier. Let's give him 10 potential energy units. Oh, and there we go. We've got the expectation value over to the right-hand side. We just had to lower the hurdle a little bit there. But anyway, you can imagine that you can make a lot of fun scenarios with this. So like, for example, let's suppose you didn't want to just have, the one barrier. Let's suppose you wanted to do a staircase barrier. So let's say that for x less than 0.25, your u was 10. And then let's say if your x was less than 0.5, your u was 5. And then let's say if your x was less than 1.0, your u was, did y'all just see the lights blink? I thought I just saw the lights blink. No. Let's say it has been raining, so I may be losing power. Let's say your u. So let's say that each time you go through this, it gets cut in half, so it's like an exponential decay. Because really, what makes this barrier approach neat is that you can approximate any other potential energy with it. Of course, if I got through the first one, it's going to get through the others. Let's increase these a little bit. Let's put it up to 20. This one up to 10. This one up to 5. Let's even add in an else if x is less than 1.5, u equals 2.5. So I'm giving it this exponential decay to it, because this is actually where you could approximate potential energies, would be to just put in a series of steps that kind of mimics the pattern that you want. Like if you're trying to solve the system exactly, or trying to solve the system algebraically, I guess I should say. So this is pretty cool. So we've got this sort of staggered step pattern. So once it gets past the first bump, it's got a pretty good probability of getting through the rest. So that's pretty cool. So yeah, I could watch wave functions bounce back and forth all day. We do need to leave this problem in the next episode so we can move on to extending this code to 2 dimensions, because so far our particle is constrained to moving along one axis. It just moves left and right. What I'd like to do next is extend this code so that the particle is moving in 2 dimensions, and that means I'm going to have to make my derivatives along the x direction and along the y direction and set up my potential energies in the x and y direction. So with that in mind, I leave you with these little vampire fang things here, or maybe they're mountains or something like that. Anyway, thank you so much for watching. I will see you next time. Bye-bye.